Hello friends, welcome to my channel. This is my lecture number 5 in the series of group theory and we are discussing about set relation function, and today we are going to discuss about function. We will see the difference between relation and function, and also we will see various facts and properties of function. So let's begin with today's video. Let A and B are two sets, then if we represent set A by this symbol and set B by this symbol, then there which is a map from A to B. Now we will see the two definitions of function. The definition number 1. It is a defined rule which maps each element of A, set A, to a unique element of set P. Then this map F will be called a function from A to B. The second definition of the function is that if for all elements say X from the set A, if there exists a unique element say Y from the set B such that this map F maps X to Y, that is f of X is equal to Y, then this F will be called a function from A to B. So these are the two definitions of function. Now we are going to see some examples. Example number 1. Let this set A is 1, 2, 3 and other set B is 2, 4, 6 and 8. If we define a map F such that f of X is equal to 2 of X, 2 into X, then this map can be represented by this figure where this is A, this is set B, and elements are 2, 4, 6, 8 from B and 1, 2, 3 from A. Then by this map 1 maps to 2, 2 maps to 4 and 3 maps to 6. So to check this map is a function or not, we will use this definition where for all elements from set A there exists a unique element from set B. So for each element from set A we have to check whether it maps to unique element of B or not. So here 1 maps to 2, 2 maps to 4, 3 maps to 6. So each element from set A maps to a unique element of set B. So that's here F is a function from A to B. If the rule from set A set B is like f of X is equal to 2 when X is less than or equal to 3, or fx is equal to 8 if X is greater than or equal to 3, then this map can be represented by this figure where these are two sets A and B and elements are 1, 2, 3 and B is 2, 4, 6 and 8. So by this map if X is less than or equal to 3 then F maps to 2. So here 1, 2 and 3, all 3 are less than or equal to 3. So all these 3 will map to 2 in the set B. So 1 map to 2, 2 map to 3 and 3 map to 2. But here X greater than or equal to 3 also F map to 8. That means 3, this element also map to this element A of 8 of set B. Now to check whether this map is a function or not, we will use again this definition where for each element from set A there exists a unique element from set B. But this element 3 from set A there exists two image. We called this element is as image of 3, where image of 3 is 2 and 8 both. That means f of 3 is equal to 2 and also f of 3 is equal to 8. That means there exists no unique element of corresponding to this element 3 in set B. So that's mean that it is not a function. But if we want to define the difference between relation and function, then we can take this element 1 and its image 2 as ordered pair, and again similarly 2 and 4 as an ordered pair, and 3 and 6 as an ordered pair, and make a set of it, say it is equal to R. Then this set will be a subset of Cartesian product of these two sets, A cross B. So by the definition of relation, this R is a relation from A to B. Also this is a function where f is a function from A to B. So we can imply that function is a relation. That means if we have given a function, then we can define a relation. But for this example, if we again make a set such that ordered pair is 1 and 2, that is element and its image makes a ordered pair, and 2 and 2 and 3 and 2 and again 3 and 8. So this is again a subset of A cross B. That means if we say it is equal to R1, then R1 is a relation from A to B. But we saw that it is not a function. Not a function. This means that every relation need not be a function. Relation doesn't imply function. But a function always implies a relation. As this is a function f from A to B, so this set, the first set, will be called as domain of the function, and this whole set B will be called as codomain of the function f. Now we are going to see some other examples. Example number 3. Let here the same example of set A, where set A is equal to 1, 2, 3 and set B is equal to 2, 4, 6 and 8, and we defined a map fx such that it is equal to 2x if x is odd. Then if you want to represent this map as the diagram A, B, 1, 2, 3, 2, 4, 6 and 8. So if x is an odd, then it maps to 2x. Here it is 1 and 3 are odd, so it will be mapped to 1 map to 2 and 3 map to 6 by this definition. But 2 is an even integer, so by this map 2 doesn't maps to any element from this set B. But by the definition of function, for each element from the domain there must exist a unique element from the codomain. But here for the element 2 there doesn't exist any image from this set B. So this is not a function. We saw two different examples that are not function. Example number 3 and this example number 2. So both are not a function. We are giving some notes here. What is a range? It is a set of elements from the codomain which are mapped elements from the domain. That means it is a subset of codomain such that it is mapped. In this example, example number 1, elements 2, 4 and 6 are mapped, but this element 8 are not mapped to any elements. That means the set containing 2, 4 and 6, which is a subset of this codomain, is called a range. So if you say B1 is a subset containing 2, 4, 6, then B1 will be called as range of this function f, and clearly range is a subset of codomain. Next, the example number 4. Let X be a set containing two elements 1 and -1, and set Y contains one element 1, and a map f such that f of x is equal to x square. Then this can be represented by diagram. This is set x, this is set y, and by this map 1 will map to 1 and -1 also will be mapped to this element 1 from the codomain y. So for each element from the domain there exists a unique element from codomain. So this is a function. Now we are going to understand what is 1, 1. It is also called as injection. We call a function 1, 1 if from the range set each element has unique preimage. Then that function will be called as 1, 1. The necessary condition for a function to be 1, 1 is that the cardinality of domain must be less than the cardinality of codomain. Now we want to see that whether our previous examples were 1, 1 or not. For this example, the first example, for each element from this range set 2, 4 and 6, there exists unique preimage for each element. That means 2 has unique element 2 preimage 1, and 4 has unique preimage 2, and 6 has unique preimage 3. That means this is 1, 1. See, it is 1, 1. Example number 1 is function is 1, 1. Now for the example number 2, this example number 4, we can see that this is range set containing a single element 1, and but this element has two preimage 1 and -1 also. So this is not 1, 1. Not 1, 1. To understand this necessary condition, we can take an example such that the cardinality of domain is greater than, strictly greater than the cardinality of codomain. Say domain has two elements and codomain has single element 1. So if this element from the definition of function, both these elements must map to some unique element of this codomain set. So if say this element map to single element here, and this element also will be mapped to this element because here is single element. So both these elements will be mapped to single element. So this is not 1, 1. Not 1, 1. That means if cardinality of domain is greater than the cardinality of codomain, then there exists no any 1, 1 map. If you want to see some method to check whether a function is 1, 1 or not, so this is the checking method. Checking method for 1, 1. We will let f of x is equal to f of y, and if we are able to prove that x is equal to y, then we will say that f is 1 1. There is some note here. If f is not a function, then we will not check whether it is 1 1 or not. If only f is a function, then we are going to check f is a 1 1 or not. Now next we will understand what is onto function. It is also called as surjection. It can be understood as for all elements say y from the codomain, if there exists any element say x from the codomain such that f of x is equal to y. That means there is no any left element in the codomain. It can be easily understood as if range is equal to codomain, then we will say that the function is onto or surjection. Now we will check whether our previous examples were onto or not. For the first example here, range set is 2, 4, 6, but the codomain is 2, 4, 6 and 8. So both these sets are not equal. So this example of function is not onto. And the second example of function, which is example number 4, here the range set is 1 and also the codomain is 1. Both are same. So this function is a onto function. For this onto function, the necessary condition is that the cardinality of domain must be greater than or equal to the cardinality of codomain. To prove that this is the necessary condition, we are going to take an example, a counter example, where the cardinality of codomain is strictly greater than the cardinality of domain here. So from the definition of function, if this element wants to map some unique element here, say the first element, and this second element from the domain say is mapped to this element, the second element, but here we see that this element from the codomain is left. There exists no any element from the domain which is mapped to this element, so this is not onto. If we map to this element, then this map will be not a function. That means if we want to map this element to this element, then this will be not a function. So we can't map this element to this element. It will be always left one element from the codomain. So this is not onto function. That means for onto function, it is necessary condition that cardinality of domain must be greater than or equal to cardinality of codomain. Now we are going to see what is a 1 1 onto function. It is also called as bijection function. A function is bijection if it is 1 1 and onto both. It is clear that if a function is 1 1 and onto, we will call that function as bijection. The necessary condition we can get from our both previous facts. Here it is 1 1, so the necessary condition is that codomain, cardinality of domain is less than or equal to cardinality of codomain. And for onto function, the necessary condition is that cardinality of domain is greater than or equal to cardinality of codomain. So if any function to be a onto and 1 1 both, then both these necessary condition should be satisfied. So any function to be 1 1 and onto both, it must be as codomain, cardinality of domain is less than or equal to cardinality of codomain and also cardinality of domain greater than or equal to cardinality of codomain. So both these conditions will imply that cardinality of domain is equal to cardinality of codomain. So this is the necessary condition of any function to be a bijection. Cardinality of domain and cardinality of codomain must be equal. Then we will check whether a function is bijection or not. This is the first condition to be checked in the process of checking bijection. If you want to see some example of a bijection, then we can easily see from our example number 1, this example, where if we take this range as codomain, that means if we take the domain as A, where it is 1, 2, 3, and codomain as the range set B1, where B1 is a subset of B and B1 contains 2, 4, 6. So here 1 maps to 2 maps to 4 and 3 maps to 6 from this definition of function fx is equal to 2x. So here this function is 1 1 and also onto, because here we take the range set B1 as the codomain. So this function from A to B1 is 1 1 and onto both, so this will be a bijection. Now moving to our next concept of counting of different types of function. So the first, if we consider the cardinality of the domain, which is here say A, is equal to n, and cardinality of codomain say B is equal to m, that means both these sets are finite, then the total number of functions from A to B will be equal to the cardinality of codomain raised to the power cardinality of domain. So for this example it will be equal to m raised to the power n, which is m as codomain cardinality and n is a domain's cardinality. So this will be equal to total number of function from A to B. Now what is the total number of 1 1 function? Total number of 1 1 function from A to B. We will count 1 1 function if the necessary condition of 1 1 function, which where that is the cardinality of domain is less than or equal to cardinality of codomain. So here the cardinality of domain is n and cardinality of codomain is m. So the condition of existence of 1 1 function between A to B is that the cardinality of domain, which is n, is less than or equal to cardinality of codomain, which is m. Then this can be given as m pn, where it is cardinality of codomain and it is cardinality of domain, and p represents permutation. This will be equal to factorial m upon factorial of m minus n. And lastly, total number of onto function. Total number of onto function from A to B. The necessary condition is that n is greater than or equal to m. That means cardinality of domain must be greater than or equal to cardinality of codomain. If this fails, then the number of onto from A to B will be 0. Similarly, in this case also, if n is greater than or equal to m, then the total number of 1 1 function will be 0. And it can be given as a formula which should be remembered always. It can be given as mc0 m minus 0 to the power n, where n is cardinality of domain and this m is cardinality of codomain. And alternatively plus minus we will write here it is plus, then we will write minus mc1, here it is 0, then after 1 mc1 into m minus 1 raised to the power n, minus, then will be plus mc2 into m minus 2 raised to the power n, then minus mc3 m minus 3 raised to the power m n, and plus dot dot dot, and in the last mc m minus 1 and into m minus of m minus 1, which will be equal to 1. That means m minus m will be 0 and minus minus plus, so it will be 1 and raised to the power n. So this is the formula to count the total number of 1 to function from a to b. It should be remembered. And in the number 4, total number of bijection from a to b. The necessary condition is that the cardinality of domain and codomain should be equal. That means here n is equal to m. Then the total number of bijection from a to b will be equal to factorial of n. It can be represented by this symbol also, factorial of n. So that's it for today. Thank you for watching.